Thank you very much for coming. This is the last seminar we have this year, and we're closing with in a high point, right? We have Alessandro Hill. Alessandro Hill is a PhD candidate at the University of Hamburg, right? And he's been working a lot of very interesting topics in combinatorial optimization, scheduling, network design. And he's going to give a talk today about ring tree network design problems. He's going to be here until January, working with Marcus and me in some scheduling problems. So if you like what you see, you can talk to him afterwards. Thank you very much, Alessandro.
Thank you for the introduction, and thank you for inviting me to give this talk here. So I'm looking forward to tell you something about a class of network design problems, which are called ring tree network design problems. And what I intend to do today is just give you a little bit an idea of how these models look like and what work has been done on these. So I will probably skip a couple of details and not go into all the methods, but tell you something about selected results here and give you a feeling about the models that we're talking about. Okay, let's start right away. And first I will tell you what the base model is. There is ring tree model behind it. And starting from this model, we derive a couple of other variants, which then I will go into more detail, which is one which augments the reliability. So we talk about reliability in these networks, then a facility location variant, and then profit-oriented models. So the base models, ring tree problems, what does that mean? Well, graph theoretically, here you see a tree on the left and you see a ring on the bottom, which could also be just a cycle. And a ring comes from telecommunications. You just use that term there. What we want to do is we want to bring these two concepts together. And we do it in the following way. Well, we can just, take a cycle and just extend this cycle by attaching trees to these cycle nodes. This gives us kind of unicyclic graphs because there's just one cycle in there. And another way of doing that is just starting with the tree itself and trying to create a cycle within this tree, meaning that we add an additional edge, which gives it a fundamental cycle. The same as we did before, just coming from a different perspective. So we can do that in several different ways, and whatever we do, we could get the cycle itself, or what we had by our extension approach in the beginning. What we say ring trees are is either such a unicyclic graph, which we get from adding one edge into a tree, or a pure tree itself. There we did not add an edge, but we could think of a trivial cycle, which is the green node here, which is extended by the blue tree that's just appended to this unique node. So these are ring trees. And this concept is useful to create a network that I'm going to explain comes from the following requirements. So we have a central node. We don't think about a specific application yet, just a central node that is distributing some information or creating some connectivity to two types of customers. The first type of customers is the type 2 customer. These are the green nodes. I will always use green for type 2 and blue for type 1. And these type 2 customers, they need to be on a ring or a cycle structure when being connected to this central node. So here we have one ring, which just collects all these customers and then creates a cycle that comes back to the central node. The other type of customers that I already mentioned, the type 1 customers, are the blue nodes here. They don't need to be on a ring structure. For them, it's sufficient to just, be within the network. For them, it's okay to be connected via tree structures. So we have these ring tree that we can use, and using this concept, we just establish connectivity within here. These blue customers, they don't necessarily need to be on trees. They could also be on rings, because we say that being on rings is something which is worth more somehow. So they could be used within the rings if it makes sense from a cost perspective. And that's already what we're looking for. We're looking for networks that are kind of cheap. So we're trying to minimize the overall cost. For modeling purposes, or just for, specific other reasons, we add Steiner nodes, which are nodes that can be used within the network, but do not have to be used in the network. So these nodes are not customers. They are called Steiner nodes because they have this certain property that you can drop them if you don't need them. If it makes sense to just route your network through these nodes because it's cheaper, then you use them. So you integrate them if just of benefit, as we see here. And this is one of the ring trees that we could come up for solving such a problem that I'm going to define here again step by step. So we want to connect all customers of type 1 and type 2 by ring trees originating from a central node, establish this connectivity, use these dyno nodes just when it makes sense from a cost perspective, ensure that type 2 customers are always on rings, type 1 customers can be on rings or on the trees, that's enough for them, and we have two types of capacity limits. So the first capacity limit is the number of ring trees that we attach to this central node, because the central node has, as a distributor, a certain limit of attached structures. And the second limit is the number of customers, not dyno nodes, that we have on each of these attached ring trees. So these are the two capacity limits that we have to respect. And the overall goal is the minimization of the total edge costs that we have in this network. We could say that there's different costs for tree edges or ring edges. That's just a little modeling trick. That's no problem. For now, we're just going to say every edge has a unique cost wherever it is located then in the end. The applications are from telecommunication networks to routing-based transportation. And what we do here is we combine a little bit two different worlds, what I'm going to try to illustrate next. So this is a solution in which we have the central node here, 3 ring trees which are, well, ring trees in the interesting way, and 1 ring tree which is a pure tree attached to it. So the capacity limit on the number of ring trees must be greater or equal to 4. And then we have a couple of different, I guess it's 20 or 30 is the limit on each of these ring trees for the number of customers that we allow in the substructures. 2 ideas for applications. Telecommunication networks. We have a central node which connects to a higher level of that will then, lead outside of the country, outside of the city. And then within this network, we have type 2 nodes, which could be a hospital, for example, which needs extra reliability. We want to put that on a ring because if just one edge fails, then there's still connectivity. It could be a police station, a university. What about the type 1 customers? Well, that's just the houses. That's normal people, as we are probably. We don't need double connectivity. It's enough to just have this fast internet whenever it is working. And the dyno nodes are just coming from the infrastructure. They give you an opportunity to just route the network maybe along big streets where there is channels already. You don't have to do any roadworks, whatever. And this just gives you a certain price that you could go cheaper by using a crossroad here, for example, which is existing infrastructure instead of, coming up with the new laying. A second thing is transportation, and then this is maybe a little bit of a childish example, but I think it shows pretty good how the structure can be used. It is 2 different infrastructures that we want to build. And here we're talking about school bus routing. So we have 1, 2, 3 different routes for the different school buses. And then the children, they still have to walk to get to one of the bus stops. And some of them, they're even collected. They're directly collected on the route, yeah? And there is some guys in Japan. One of his names is Kenichi Kanata, and he worked on safe school bus routing walking tours. So he was saying that these walking tours here, you prefer to just, somehow make the children walk as long as they can together, as you can see here, because that's safer than having them walk all alone this way. So this just, people think about how the walking ways are to these bus stations. So you can combine this, have 2 levels. In the first infrastructure level, you just think about, well, minimize somehow the cost or the distance that the school bus does. And in the second, you say, well, there's some walking distance which is bounded. Then you have maybe a bound on the number of pupils that you can collect by a bus in total. And then you're pretty close to what this model does. Okay, this just to give you an idea. But what we do here, there's an elegant thing with this model. We're just somehow connecting trees and rings in a combinatorial optimization problem. Yeah?
Just one question. So the rings need to be disconnected?
They need to be disconnected. We want the single ring tree that we had in the beginning, we want a couple of those being attached to the central node. There is no way of connecting these. No, they can't. Exactly. No, the structure, the topology is always a ring extended by trees or a pure tree. So, yeah? So basically, we're looking at minimizing the overall cost, but in the next topic that I'm going to touch, we're going to see that multi-objective approaches are very common and are natural, kind of, because you're doing this multi-layer or multi-step optimization model. In this model, what we're doing is look at these 5 different problems. On the left, you have a problem which is 100% type 1 nodes, meaning there is no extra reliability required. And on the right, you have the other extreme in which every node needs to be on a ring. And what we're doing is we're doing things in between. Yeah? Let's just say that we increase the rate of nodes that need reliability from left to right. And if we solve these problems to optimality, we see that from a pure ring solution, a tree solution, we just gradually, change to a ring-based solution, which looks like a vehicle routing solution in this case. And in between, it depends on the configuration, the costs, and certainly the number of nodes of each type. Then you have a couple of different structures, and the overall solution then changes. And the cost is definitely a non-decreasing function, because with additional reliability, a ring that you want to install, you have to close a ring, which is more expensive than just the tree structure with branches out. Yeah? No, that's a bound. That's an upper bound on the number of ring trees and an upper bound on the number of customers that you allow on each of these ring trees. That's the two capacity bounds. You could fix that. That's an easy thing in the model, yeah? So there's related models. We generalize a lot. For example, the vehicle routing problems with unit demands. If you look back here to this right picture here, that's a vehicle routing problem with unit demands. We're just more on the counting side. We're not doing continuous stuff yet. That will be an extension. Then capacitated Steiner or spanning tree problems, which is just, if you look here on the left, these are spanning tree problems. The capacitated spanning tree problem is very famous. It was there for a couple of years. And we also have capacitated ring star problems, which are not that old. And these ring star problems are very much related because they don't allow the extension of a ring by a whole tree structure, but just a single assignment, which looks like stars then. And there is low connectivity survivability network problems. And these problems are maybe a little bit related to what you just said. You don't give a structure, but you just want a certain reliability. So you say that you want 2 paths from each type 2 customer going to the depot and 1 path, at least, from each type 1 customer to the depot. Okay, so we generalize a couple of these, the vehicle routing problems and the Steiner and the spanning tree problems, the capacitated ones. And there's a couple of work regarding algorithms done on this. Since we introduced this model, it's mostly us who worked on this, but we're looking forward to other people to start maybe using this model. So we came up with a cutting plane method, which was the first approach that we did for getting optimal solutions to this problem. And then what we also did is designed a branch and price algorithm, which just based on a different formulation. And for all these, we need simple heuristics, local search heuristics, which are meta heuristics. So I implemented a version of a iterated multi-start local search algorithm, which just gives initial solutions and gives us an idea of how hard these problems are for these classical heuristic approaches. And then we stepped over to math heuristic approaches, which are a combination of these classical meta-heuristic approaches in a local search fashion with mathematical programming tools. And these are the most powerful tools that we have for this problem at the moment. So I give you a brief idea of what the results look like. I derived instances from the TSP-lib. So I have 225 instances, and they're up to 100 nodes with different customer rates. So we have different distributions of blue and green nodes and different capacity combinations. And the cutting plane method here solves 55% of these problems and an average optimality gap of 2.6%. The limit, more or less, is at 50 customers. That's what we can do, which is pretty good when we look at how we started. We started with just 20 nodes, was real hard. Then when adding all these cutting techniques, we got better. Extending that by heuristics and fine-tuning it, we came up to 50 customers. But above that, generally, it's not good for us. It gets a little bit easier in these extreme cases when there's just one type available. Then we could solve more if we are exactly in that transition phase where we say we want to decide whether there's cycles or trees or both. The branch and price approach is something that we're still working on. We got really good lower bounds, but the runtime is a problem because the pricing problem is real hard, and the pricing problem will be something that I'm going to talk about later that we had to work on because it appears here as the pricing sub-problem. Then the meta heuristics give pretty good solutions, but to be honest, I put a lot of effort in there. It's not just shifting one node, it's a couple of complicated operations that are undertaken, and then you can get an average gap of 3.2%, which is not that bad if you compare that to our exact approach. The math heuristic then is capable of improving 61% of the heuristic solutions on 1.3% on average, which is a low portion, but it is more for getting to that high end, trying to get it as good as possible by investing a little bit in terms of runtime and in, the complexity of the approach. But if you want to get up with your with the quality of your solution, this is a way of doing it. That's what we wanted to show. So this is just the results table, which gives you an idea of what we did on it. Please.
So did you use a specific solver for solving these models, or just you implemented the code by yourself?
So for the cutting plane method, we used the branch and bound framework by Cplex, and Cplex as a linear programming solver. For the branch and price, we did it in Skip and exchanged different linear. We did Soplex and Cplex. For the meta heuristic, that's 100% my code. And for the math heuristic, we also used the cutting plane method as a subroutine in these procedures, which has the same functionality as for the exact approach. Okay, let's go to another topic. I mean, this is a topic that somehow emanated from this. So we're thinking about telecommunication networks, and in telecommunication networks, we already got an idea. Reliability is something that people are concerned about. Let's think about this one edge failure scenario. So the ring tree problem is something that actually helps you out if you have fear that one edge is going to fail, because all these nodes, customers on the rings, they're safe. Right? Nothing's going to happen. So the model itself is kind of oriented versus the one edge failure. Let's assume that this one single edge is going to fail, and that the probability of failure is, uniformly distributed, such that each edge fails with the same probability, and the nodes are perfectly reliable, meaning that the nodes are never causing any trouble. It's just the edges themselves. Then we see that the tree customers, they might get disconnected, right? In this case, which is going to happen, one edge fails. The tree customers are kind of the ones we have to take care of. The ring nodes are never affected. So let's look at this example solution here. And we know that each tree customer could just fail because, could just get disconnected because one of the critical edges fails. So instead of designing the network in this way, we could maybe come up with a network that includes more of the customers, of the blue customers, in the ring, right? So here, for example, customer 3 and customer 7 they're safe both, right? But we pay for that. Obviously, I mean, that's not going to be cheaper than what we did before. And the best what we could do, well, let's just put them all in a ring, right? And then we don't have to deal with these kind of issues anymore. But that's going to be the most expensive solution for this. So an alternative objective or an additional objective would be that we minimize the number of tree customers, right? I mean, just pull them into the rings. And in this model, it's nice because you can change the situation of a customer. You can put it in a reliable situation coming from outside, which means the tree here, the second level. Let's look at the tree edges. I mean, it could be that we have more edges in here that in these sub-trees than we have customers, because we allow Steiner nodes. So here we have, how many edges do we have here? We have 1, 2, 9 edges in here. And maybe it would be better to not use the Steiner nodes, because we have less edges. We just save 2 edges, 7 edges. And 7 edges means that, wow, there's less edges that can fail, that can contribute to disconnecting, for example, the last customer that we have here. So minimizing the number of tree edges is another objective that we could look at, closely related to what we had before, but a little bit different from a combinatorial point of view. And another one, so, okay, this is the best that we can do, because, I mean, we're just putting everything on a ring, and then we're good with tree edges or tree customers. And another thing that we could look at this example here. What's the problem here? There is one critical edge, which is super critical, right? And this is the one that connects all the tree customers to the ring. Actually, we don't want that. Maybe we're better to do something like this. This would be a ring star, by the way. Okay, so now in every case of this single edge failure, there's just one customer that this gets disconnected. That's not too bad, but it's going to be more expensive. That's easy to see. The best, again, well, yeah, just put them on rings, then everything's safe. Here, we're minimizing the number of customers on a subtree, which is edge-induced. That's important. Edge-induced and attached to the ring. And I'll give you a fourth idea of what we could do to increase the reliability of the tree customers in these networks. And this is, let's look at this example. Right? It's a little bit similar to the one before, right? If we cut off this edge here, then everybody is disconnected. Every tree guy is disconnected. But it has a different structure, and we can think of it from a different point of view. So there is the leaf customer here, which is customer I. Customer I gets disconnected whenever one of the edges that connect it on the path to the ring fails. So there's a length of this path, and the length of this path is called in telecommunication networks number of hops. And these are the number of tree hops that connect a customer to a ring. So if we have more hops, well, that increases the probability of this customer being disconnected, right? So we want to minimize these hops. What could we do? Well, again, it's closely related to what we have before, but although it's different. So it would be nice to just, hop number one, okay, and then this is the best that we can do without going to what we had 3 times before already, just doing everything ring-based. So these are 4 objectives that we could look at. And what we did is we created, please? Yeah.
So key, for example, just to be sure.
Yeah.
This solution probably is the optimal for minimizing the tree edge. So I was thinking you have, for example, a client that probably you can connect it like a tree.
Yeah.
Using a lot of edge.
Yeah.
Minimizing the tree hops, or connecting in a path, minimizing the link edge, but maximizing in some sense the tree hops. So that your objective are
maximal tree hops here does not mean maximizing the tree. Okay. Yeah.
Suppose that you have some client in a tree.
Yeah.
Binary tree. That minimize your distance to the ring. Okay. That probably is the.
Well, it would be even better to do it this way, or not?
Yeah. Okay. Let's do it like that.
So here's always the costs versus this. It's a min-max here. In this and the previous case, the maximal number of hops of each customer, and that's automatically a leaf customer because every other customers have less max than the leaf customer. So what we did is we just created bi-objective problems, each of them having the cost function as the first objective. So we're still interested in the cost of the overall network as we were before, but we add one secondary objective, which could be one of the 4 that I just introduced here. So these bi-objective problems, we solved this to optimality. That's what we did in this work. And we come up with a branch and cut algorithm, which is based on a multi-commodity flow formulation. And there, multi-commodity flow, because you can integrate a couple of additional constraints. So if you then, want to compute such a minimal set of efficient points, then what you need is you have to efficiently, navigate through the solution space. And this is done by just integrating bounds for all these secondary objectives, which lead to problems which are known in combinatorial optimization. For example, there is hop constraint spanning tree problems. And here you have a tree hop constraint capacitated ring tree problem. And the same is that you have the number of subtrees, customers in a subtree limited. You have a problem which tells you that the capacities to trees attached to the rings is just limited. And by this, you can navigate through your space here and compute these Pareto fronts. And I'm going to give you an idea what this looks like. So it is an iterative strategy, and it uses heuristics, and is actually quite sophisticated because the problems get so hard by adding these, easy to understand additional constraints. So this is one example I took out because I thought it's nice to see. We look at cost versus D, which was the maximal number of hops here. And from left to right, from top to bottom, we see a minimal set of efficient solutions. So the first one here minimizes the cost, the overall cost, and has no bound on the maximum number of hops. Then you get a network which looks like this one here. And I show here in orange, which is the worst hop path that we have for this leaf here. We have a length of 9, and that's something that we maybe don't want to live with. So we could say, okay, let's invest a little bit more then we pay 246, and we have a maximum length of 8. And you see it's pretty easy just flipping this customer and attaching it to the other tree. And then you just, I mean, you pay 1 unit more, but you get a better reliability if you're concerned about your maximum number of hops. And so on. If you do that, you just increase your costs by reducing the maximum number of hops that you have in your trees. And at a certain point, look at the red one here, it switches to, from now, I install rings. It makes sense to install rings because installing rings gives a certain safety. These customers are just taken out of the danger zone. There's nothing wrong with them anymore. And we have to pay more, which is 299, but get a maximum hop number of 3. That's the good thing. And then from here on, what we can do is we can proceed and see that if we really want to, minimize that as good as we can, that secondary objective, then we have to pay 328, which is significantly more than the 245 if we wouldn't care about this objective. But we end up with a solution as expected, which is purely ring-based. And here we have, again, the transition from a tree-based model, tree-based topology, to a ring-based one. And in between, we're just taking care of the secondary objective, which could be exchanged by any of the other 3 that we have. Does that make sense? Okay, and I'll show you some of the curves here, just to give you an idea of, for these test instances, how these values then are computed. So we see that this is an instance with no type 2 customers, so everything should be tree. And we can see that these 2, red and blue, red is number of tree customers, blue is number of tree edges. We saw that they're kind of related. And green and what's that color? Oh, good question. Green and brown is the other 2, which was the maximum number of subtree customers and the maximum number of hops that you can find in a subtree. So you see that they're closely related and therefore kind of have different paths here in this diagram. Yeah?
The vertical axis is cost.
The vertical is cost, and this one is the counting one, which tells you the secondary objective. In one case, it's the number of, here in red, it's the number of tree customers. So 12 tree customers is what you do with paying the least, and then you can do, 5, but you have to go up to 190 cost. And you can use the same value because everything's counting based for the number of hops. So the number of hops here starts with 5. And if you want to get rid of a couple of hops, then you have to, increase your cost by just going left. So the nice thing is here, we have the cost, the continuous cost objective, and we have the exchangeable counting objectives, which are reliability oriented. And I'm sure there's many others that you could come up with, because if you just look at this one here, this example here, you have 1, 2, 3, 4 customers that have 4 hops to the ring or to the depot. What's better, having 5 and just 1 of them, or 4 with 4? So there is still things that you could think of where there's other objectives that you want to integrate. Okay, so this is the thing that I wanted. Please? Yeah.
So how much harder would the problem get if you let the probability of failure to vary across edges?
We didn't experiment with that. With most of it, we just stayed, good idea. From a computational point of view?
No, even from
to be honest. Yeah. That would be a very natural extension. If you want to go to practice with this, you cannot do that much. Yeah? You would have to go to something as you did. We didn't start thinking about that yet, because actually it was we were struggling a little bit with coming up with something that makes sense in this way. And what we did is we said, what would happen if nodes fail? That's another thing that we looked at. And we did the same thing and saw that it is quite different if we let the nodes fail, because the models and the subproblems become others. But we didn't do what you suggested. It would be a nice thing to think about and go in that direction.
I was confused by this comment.
Oh.
I don't see where the problem comes into place.
It doesn't. It doesn't. But then it would.
No, but I think it doesn't come into play because it's the same for all places.
here you're considering for different second objective function, and either of those depends on the probability being the same.
Just count the number
of course, you could come out with a new objective function or secondary objective function where, I don't know, you minimize
different. Would come into play.
Yeah, you would just start from a different base model, which would say that there's different probabilities on the edges. And then you get 4 different biobjective problems. Yeah?
More or less, if you're using a bound for the reliability, it will be equivalent to a uniform failure for links. The same failure for every link and independent. I think the model covers that model. Just to have to rename links.
That's an interesting thing to think about. I think that's really worth, because that's more practical, right? So, yeah. What's the next thing that I wanted to show you? That we did think about these. It's a bi-level problem. So in the first level, we designed the rings. In the second level, you could think of it, we designed the trees. And if you do it this way, then there's a natural extension which tells you there must be something that you need to do to combine these two infrastructures. This integrated decision-making, I mean, has a certain cost in terms of that there's facilities that need to be installed wherever you attach a tree to the ring, right? That could make sense. And in telecommunication networks, that could be a certain splitting device on which you maybe change to a different kind of cable that you use, copper to fiber, fiber to copper, or just because you need to split, there is just extra effort that you put in there. For the school buses, it could be where the bus stops, right? Where do the children wait? There needs to be something installed in there. So we now say that we have a capacitated ring tree problem, but we have facility installation costs for each of the nodes, could be a Steiner node or any customer that is used to attach one of these subtrees. And if we do that, we can exactly model these infrastructure changeover costs. And since we're talking about facility installation, it makes sense to introduce additional capacity constraints. And these affect the number of customers that are allowed on the subtrees, because a facility does always supply, right? And it supplies the customers on the tree. So this is a new limit that we introduced, the third one already. And let's look at a solution, how it changes then. So the red squares here are installed facilities that are just necessary to, for example, here, I mean, facilitate the subtree. We have another one here, and in the, remember about the school bus routing, then this would be bus stops, because all the other children that are picked up at home, they don't need a bus stop right in front of their house. Well, they could request it, but I think it's okay to wait inside. Yeah? But the others, they have to walk a while, and they arrive here, they want to wait here, they want to see the timetable, whatever, and therefore you have to install something there. So this is the facility location version of it. What we did is we formulated that using a commodity flow formulation and an extended formulation based on a set partitioning model, and to just try to compute some bounds and see how much harder that gets, because this model is more complex than the previous one. And what we did so far is just compare these two formulations and saw that, as expected, this set covering formulation is much better in terms of lower bounds. And the instances that we derived from this TSP lib-based set, and we could just solve 25% of them. But there's complicated pricing involved, and this is something that we're still working on. However, we already presented it at the Lagos just as a model. This was the quickest section, and the last one's going to be one where I'm going to go a little bit more into computational details in the end, and this is something that we're currently working on, which is I'm putting the main focus on. So let's just change to directed models in this case. Let's say that we don't have trees, we have arborescences. So an arborescence is just a directed tree, which we root here in one of the green nodes. It's very similar to what we had before, just that we have arcs instead of edges. And then we have circuits, which replace our rings. We could still call them rings. We could still call them cycles, directed cycles, dicycles, whatever. And we want to bring these two together, leading to pseudo-arborescences, which is something like a pseudo-tree in the directed case. And again, we take these things together and say these are ring arborescences. You know, it's just a directed version, nothing real super fancy, but it's more general. So we cover, for example, asymmetric costs. That's really important. And we want to use that as a starting point for something which brings profits, past customer profits into play. This base version, you can call it a ring arborescence problem instead of the ring tree problem. What we want to do is assign a profit, PI, to each of the customers in the network. Not the Steiner nodes, they're just auxiliary, they're not really needed, it's the customers. And then, I mean, you could think of that customers that are of type 2, these reliability important ones, have a larger profit than other ones. But this is just, I mean, instance dependent. So there's 3 versions of profit-oriented models that we came up with. And the first one is the price collecting one. Price collecting is a concept which is used in tree-based model as well as in vehicle routing problems already. So we just elevated that to this more generic model. And this means that we minimize the ARC costs minus the collected profits. Yeah, so we just want to, I mean, spend as least as possible by just taking into account the profits. And the second version is that we have a target profit that we need to achieve. And we want to minimize the ARC costs. So doing that in the most efficient, cost-efficient way. But target profit, this is what we need to make. And we want to minimize our expenses on the network. And the third one is kind of contrary. It says there is a budget that we have, a budget for laying the network, but we want to maximize the profit, the overall profit that we get by collecting the customers, while not spending more as we have given. So these 3 models then, I mean, lead to different solutions. If we look at this standard solution that we had a couple of times right now, we see that, okay, not all customers need to be connected within the network. This is one thing. And it could look much different than the overall solution. It doesn't necessarily need to be a subpart of what we had. It could be a totally different topology, and it could be small. It could even be an empty solution, for example, if we do not have a target profit. Then an empty solution would even be feasible. So what did we do here? Well, again, we started with some heuristics. You need to somehow, yeah.
You either don't consider them, or if you consider them, you have 2 paths.
So it is still, you have all the customers given as before. Now you can decide which customer you want to connect within the network. If it is of type 2, green, it has to be as before on a ring. If it is blue, it is either on a ring or on a tree. And if it's a Steiner node, well, do whatever you want with this node. So the requirements are the same. The only option that you have is dropping one of the customers. For example, if you look at these customers here, they might bring you a little bit more profit, but they are very remote. So it could make sense to say, I'm going to stop my structure way before this, these outskirts here. And I'm going to cut off this one too because it doesn't make sense. And that's exactly what you did here. You said, no, these ones, it's not worth going out there and collecting the profit because it's too far away. It's too costly to get there. And the same here for this whole suburb, for example, if you think about it geographically. The suburb is just, it's just not worth being explored. Sorry, that sounds a little bit harsh, but it is profit-oriented. Okay. And what we did is started with local search heuristics, and the local search heuristics are very much related to what we did for the original version of the problem. So you can do reconnections, insertions, extractions, removals. You can just take any node and try to put it somewhere else, which is very complicated because you have different types of nodes, different types of situations of the nodes. It can be in a ring, you take it out of a ring, put it in a tree. Take it from a tree, put it in a ring. That's a lot of hands-on work that you need to do there. However, I have 8 or even more of these local search procedures that you can run once you implemented them. And then we did the exact formulations. And it is together with Roberto Baldacci and Edna Hoshino that we're working on a couple of different formulations. What we want to do is for this version really try to find out, I mean, how strong these formulations are. And we started with the arc-based cut set formulation, which is basically derived from the initial formulation that I set up for the capacitated ring tree problem. And we also thought about a multi-commodity flow formulation, and we have ready a set partitioning-based formulation. And there's a couple of variants, especially when coming from routing. There's a lot of work that has been done on exact approaches, and we're trying to integrate these state-of-the-art methods based on certain formulations in this more generic problem here. That's our current work. So there's more formulations that we're still working on. And we already implemented many of the inequalities that we could come up with, and these inequalities apply to several of the formulations. And They are very important for the practical performance for exact algorithms. So we have connectivity inequalities, which are known, and capacitated connectivity inequalities. Everything comes with capacity in these models. And we also have inequalities that come from the circulation, which is the rings. We have stuff that comes from the trees. We have stuff that combines these things. And there's a lot of room for thinking about ideas that you could integrate there and derive from concepts that you have for tree-based models or ring-based models. So I'll give you a couple of results for this problem using this arc-based cut set formulation. So let's see on the left upper hand side, we see that this is the price collecting version, the budget constraint on the right, and on the bottom, the target profit. And these are the instances that we could solve. So the vertical axis shows the percentage of instances solved. And then I split it up in the number of nodes in the network, 26, 51, 76, comes from the depot plus 1. And this z-axis shows the distribution of, or the rate of the customer types, because we saw that it makes a difference whether you're just looking for rings, just looking for trees, or somehow in between. So if you have a 0 here, this is the type 1 rate, then you are exactly at the ring-based problem. And at the bottom here, in the back, you are at the tree-based model. So
you're plotting the number of instances solved to optimality, or
solved to optimality within an hour. This is an hour, and which ones I could solve to optimality using the first formulation. And it is substantially supported by heuristics. It does local search whenever the incumbent is replaced as a starting solution. It utilizes a couple of Cplex features that I turned on. So this is the best that we just can do right now. And using everything we have. And we see that, okay, I mean, from these small ones, 26, we can solve them all. Here, the black towers are is the total, and 72% of the still small ones with 50 nodes, but which is not that bad. And if we go up to 76 nodes, then it's just 15% that we could solve. We see that the hardest are the ones in which the decision has to be made whether you want to install a ring or a tree, because you have nodes of different colors. That makes it more difficult. So we see a similar picture here for the budget constraint and for the target profit. So that doesn't seem to make a huge difference. We just have to somehow deal with these gaps here in the middle, which come from just the combinatorial hardness of these instances, at least.
Which formulation was that?
Pardon?
Which formulation was this?
This is the arc-based cut set formulation, which is basically directed Steiner tree problem formulation, and then you route a circulation through your rings. So you have variables for the circulation flow, and that's it, not more. If we look at the optimality gaps, well, certainly for the small instances, they're 0. And we see that's complementary to what we saw before. Yeah. So the optimality gaps, that means after an hour of runs, this is what we have as gaps. But it goes up to 8% for the 50 node instances and 37% for the 75 node instances, which is rather high. And this is something that we definitely still need to work on. But it's just that the instances are getting real hard at this size. It's just a problem. And the branching nodes, we see that there's a lot of branching done here on the outside, less branching in the middle, because also the linear relaxation maybe is harder to solve. And the runtimes, I mean, it's clear that the runtimes are getting higher the harder the problems are. And the root node gaps somehow shows a similar picture as the optimality gaps. So here, there, it looks kind of consistent. Yeah, we're finalizing the comparison of the formulation, trying to work on that during the next month, derive a couple of further inequalities. We're not sure about whether we can apply them or not. And an important step would be to develop more powerful heuristics on these problems, because you need to come up with some new concepts. You cannot do local search. You could do something like random heuristics or like that, but I would say that there's a lot of work implementing them for. I'm not convinced that you get out something which is real powerful, because the combinatorial structure is challenging for these these problems. And then we wanted to put the work together and just do some branch and cut and price to just, further improve this exact approach and try how far can we get with combining these two different formulations. That's everything what I wanted to show you about rings and trees. If you want to, discuss any topic, feel free to ask me, and I want to thank you for your attention.